Hello, good morning, my dear students. This is again your Virat Kumar, lecturer in Electrical and Electronics Engineering from the college or the Institute of Government Polytechnic Vaddepalli with the semester of 4 and with the subject of AC machines. And it has the SPTT code given by 18EE403C. And the topic is single phase transformers. And here in the previous class, nothing but the 28th PPT, we have seen the load sharing between the two transformers of the derivation, and today we'll be seeing about the problematic involved in it. The problems involved on load sharing between transformers. In the previous class you have learnt about parallel operation of transformers. In that we have seen some formulas of IA is equals to I into ZB by ZA plus ZB. Similarly IB is equals to I into ZA by ZA plus ZB. And the load shared by the transformer A is SA is equals to total S into ZB by ZA plus ZB. Similarly, the load shared by the transformer B is SB, that is equals to S into ZA by ZA plus ZB, where X is the kV of transformer, Z is the impedance, ZA is the impedance of transformer A, and ZB is the impedance of transformer B. Once you just make a note of these four formulae so that we can directly step into the problems so as to solve easily. Just make a note of that. Both IA, IB, SA and SB, where IA, IB are the currents of transformer A and transformer B, and SA and SB are the kV of transformer A and transformer B. Okay, fine. Now, upon the completion of this topic, the students will be able to know about how to solve the problems on load sharing between the two transformers. So, directly stepping into the problems, see the problematic over here. Directly we'll do the problem, since we have seen the derivation part in the previous PPT, and also we have cross-checked the formulas, and now we'll move on to the problems. Simultaneously you just note down the question and also the solution of the load shared by the two transformers. Firstly, see, two single phase transformers work in parallel to supply a load of 750 amps at 0.8 power factor lag, and the voltage ratio is 11,000 by 3,300 volts for each transformer. With HV winding short circuited, the SE results are transformer A has the following data of 200 volts, 400 amps, 15 kilowatts, and transformer B has 100 volts, 400 amps, 20 kilowatts. Now determine the secondary voltage. Determine the secondary voltage, the output and power factor of each transformer. Determine the secondary voltage, the output and power factor of each transformer. Just read the question carefully, try to analyze it, and also try to make the given data. Or else let us see it. The given data over here is, we have the load current IL of 750 amps at 0.8 PF lag, and we have E1 of 11,000 volts and E2 of 3300 volts. The transformer is secondary input. Since this is a high voltage in the primary, so the transformer is secondary input is that, but since it is short circuited, so the secondary input is 200 volts, 400 amps, 15 kW. The transformer B has a secondary input of 100 volts, 400 amps, 20 kilowatts. This is the given data. 200 volts, this is a 400 amps and 15 kilowatts. The transformer B has 100 volts, similar 400 amps and 20 kilowatts. And here the given data is finished, and the required data in order to find is the secondary voltage V2, the output, and also the power factor of each transformer. Also the power factor of each transformer. And the formula for the secondary voltage V2 is E2 minus IAZA. E2 minus IAZA. Now from the SC data of transformer A, the short circuit data from the SC data of transformer A, we know that ZA is equals to VSC by ISC, that is equals to 200 by 400, which is equals to 0.5 ohms. And now we also know that RA is equals to WSC by ISC square, since WSC is equals to ISC square RSC, nothing but RA. So from that, RA is equals to WSC by ISC square. So from that, 15, since it is 15 kilowatts, so 15 into 1000 by ISC square, 400 square, that gets 0.94 ohms. Now we have ZA and RA, and we can find XA easily. XA is equals to under root of ZA minus RA whole square. That's simply under root of 0.5 minus 0.094 square. That finally gets 0.491 ohms. And we can also find the power factor angle pi a is equals to tan inverse of XA by RA. So from that, tan inverse of XA value is 0.491 by RA is 0.0. 0. It is 0.94 over here, it is 0.094 here. You please just calculate it, whichever is the right one, and you just note down that one, and you will be getting the value of pi a of 79.1 degrees. So for this, if you just multiply directly with cos, you will be getting the power factor of transformer A, isn't it? And now from SC data of transformer B, similarly ZB is equals to VSC into ISC is equals to 100 by 400 is equals to 0.25 ohms. Similarly, RB is equals to WSC by ISC square is equals to 20 into 1000 by 400 square is equals to 0.125 ohms. And similarly, XB is equals to under root of ZB minus RB whole square. We will be getting 0.2165 ohms. And we have all the parameters R, Z, R and X. Now we can find the value of pi B is equals to tan inverse of XB by RB, that is equal to tan inverse of 0.2165 by 0.125. Then you will be getting 60 degrees. Note it down. Just note it down clearly. Okay. Now we have a pi A and pi B. We can find the power factors separately to both transformers. And before that, we have ZA plus ZB is equals to ZA is equals to 0.094 plus J 0.491 plus 0.125 plus J 0.215. And if you just this is a rectangular form, if you just solve it directly from giving the inputs to your Casio, the answer is yes. Similarly, IA is equals to total I into ZB by ZA plus ZB, as we have seen these formulas in the starting introduction class. So we have total I 758 an angle of minus 36.86 into ZB is this one, should be converted into polar form. Z is plus ZB is this total in the polar form, and you will be getting 253 at an angle of minus 49.6 degrees. Let's make a note of that. And moving on to the next slide. 3300 at an angle of 0. Just make a note of this. IB by IA is equal to ZA by ZB, and IB is equals to, from this we can write IA into ZA plus ZA by ZB, and we have all the values of IA, ZA and ZB. Just put the values in the Casio by fixing it to complex form, so that you will be getting 506 at an angle 30.5. The secondary terminal voltage V2 is equals to V2 at an angle of 0, and let us consider E2 is equals to 3300 at an angle of 0. Next we know that V2 at an angle of 0, that is equals to E2 at an angle of D minus IAZA, that is V2 at an angle of 0 is equal to 33,000 at an angle of D minus IA value is 253 at an angle of minus 49.6 into ZA is 0.5 at an angle of 79.1. Now V2 plus J0, this if we just write it as 3300 cos D, let us assume that the angle be D cos D is 2 plus 3300 sin D minus, if we just multiply both these things, we'll get 110 minus J 62.3, and equating real and imaginary terms separately, we'll be getting V2 is equals to, these are the real terms, cos, the cos terms are the real terms, the sin terms minus J, which is a imaginary term. So V2 is equals to 3300 cos D minus 110. Similarly, this 0 is equals to, so we have separated imaginary terms and real terms. and the real terms as equation 1 and the imaginary terms as equation 2. Now dividing equation 2 by 1 is equals to, we'll be getting 70 is equals to 62.5 by 3300 is equals to 0.0189. B is equals to, if we just sign inverse, then we'll be getting 1.08. And now V2 is equals to 3300 cos D minus 110. Now substituting value of D in it, we'll be getting the value of V2, 3189 volts. And then output of the transformer A is equals to SA is equals to V2 into IA. That V2 is 3189 into IA is 253 at an angle of minus 49.6. That gets 807 at an angle of minus 49.6 kVA. Just make a note of that. And now the power factor of cos pi A, we have the value of pi A, and if we just multiply with cos, we'll be getting the power factor. That is cos 49.6 is equal to 0.648 lagging. The output of transformer B, SB is equal to V2 into IB. V2 is 3189 into 506 at an angle of minus 30.5. That will be getting output of transformer B, SB is equals to 1614 at an angle of minus 30.5 degrees kVA. The power factor of cos pi B is equals to cos 30.5 is equal to 0.86 lag. So this is the entire problem structure. Like we have found the value of V2 outputs of transformer A and B, and also the power factors of transformer A and B. Okay, now moving on to the next slide. It's problem number 2. The two single phase transformers with an equal voltage ratio are running in parallel and supplying a load of 100 kilowatts at 0.8 power factor lag. The equivalent impedances of the transformers as referred to secondary are 0.5 plus J 3 ohms and 0.6 plus J 10 ohms. Find the load shared by each transformer. He's just asking the value of SA and SB. So simply the SA is equals to total S into ZB by ZA plus ZB. If it is for SB, then S into ZA by ZA plus ZB. So firstly we need to find total S, that we have kW and power factor, and if we just divide it 100 kW by 0.8, we'll be getting kVA. No, I think it's multiplying. Then we have ZA and ZB as usually. So it is very simple problem. See the given data. ZA, the impedance of transformer A, that is ZA, is equal to 0.5 plus J 3 ohms, and the impedance of transformer B, ZB, is equal to 0.6 plus J 10 ohms. And the power factor cos by is 0.8 lag, and we have the pi cos inverse of 0.8, 36.86 degrees, and the total load is of 100 kilowatts. And we have the value of S is equals to kW by cos pi, as I've said you, kW by cos pi 100 by 0.8 at an angle of 30 minus 36.86, since we have this angle lagging, so it is minus, so that is 125 at an angle of minus 36.86. Just make a note of this. This we need to find now the load shared by the transformer A, that is SA, and the load shared by the transformer B, that is SB. These are the two things which we need to find. And simply we have the formulas for SA is equal to, as I have said you in the previous, S into ZB by ZA plus ZB, and similarly SB is equals to S into ZA by ZA plus ZB. So it is very clear that we have the value of S, ZB, ZA plus ZB also. So it is very simple, we need to just substitute the values in the Casio and provide the answer. Just make a note of this. And you just try to substitute all the values and solve it. If it is not happening with you, then we'll see the answer. You just try it, or else we'll check the answer. See the solution. The load power factor cos pi is 0.8 lagging, and pi is cos inverse of 0.8, that is 36.86, and we have the load shared S is equal to 125 at an angle of minus 36.86. And the percentage impedance of transformer A, ZA is equal to 0.5 plus J3 ohms. This is in rectangular form and we need to convert into polar form, that is 3.04 at an angle of 80.53. This can be done simply by entering the values in your Casio by putting the mode in complex form. So that if all the values are in polar, that will be very easy for us to entry or to calculate. So AC is also in the polar form. If it is represented in angle, that is called polar form, and it is represented in J notation, then it is called rectangular form. Please make a note of these. Similarly, we need to make the value of ZB also into rectangle form to polar form. You can see the percentage impedance, not percentage impedance, just an impedance of a transformer B. ZB is equals to 0.6 plus J10 ohms, and converting that into polar form, we'll be getting 10.02 at an angle of 86.56 degrees ohm. And now we can directly substitute, or else we can find first ZA plus ZB as a common factor, one factor, that is 0.5 plus J3 plus 0.6 plus J10. Directly substitute in your Casio, so that you will be getting in the rectangular form. Since the Casio's answer bar is designed for rectangular form, and after that we need to convert into polar. Simply we need to shift 2, 3. Press shift 2 and 3. We'll be getting the polar form. That is 13.5 an angle of 85.16 degrees ohm. Just make a note of them. Load shared by the transformer A, we have directly the formula SA is equals to S into ZB by ZA plus ZB. Directly substituting the values, we have the value of S 125 at an angle of minus 36.86 into ZB value is 3.04 at an angle 80.56 divided by, in total ZA plus ZB is 13.5 at an angle of 85.16, 85.16. Then you'll be getting the answer as 29.12 at an angle of minus 41.49 degrees kVA. Please make a note of that. Make a note of this. After that, we need to do low shade by the transformer B, that is SB is equals to S into ZA by ZA plus ZB. That is, again we have the value of S, that is 125 at an angle of minus 36.86 degrees, into the value of ZA is 3 into 3.04 at an angle of 80.56, divided by in total of ZA plus ZB of 13.5 at an angle of 85.16. If we just solve it directly, you will be getting 104.93 at an angle of minus 27 degrees. Just please make a note of this, and once go through the entire problem. If you have any doubts, you can just raise in the comment box. So next, in this period, we or you or we all have learnt about how the given load is shared between the two transformers. Okay. So this small quiz which is being conducted over here. So just make it. For paralleling the two different rating transformers with same transformation ratio, their equivalent impedances must be dashed to their rating, direct proportional to the rating or inversely proportional to their rating. I think this one was discussed in the last PPT of number 28. So I think you can guess the answer. Take a couple of minutes time and post your answers in the comment box. Once again, I'll just repeat the question. For paralleling the two different rating transformers with same transformation ratio, their equivalent impedances must be direct proportional to their rating or inversely proportional. Just think and guess the answer. From my side, my answer is inversely proportional. I hope you are also guessing the same answer, which is B, which is inversely proportional, which we have seen in last class, last PPT of number 28, 18EE403C dot 28. So you can check the answer over here, which is inversely proportional is the right answer. Inverse proportional is the right answer. Just make down this question. Okay. Moving on to the frequently asked questions. Nothing but we have the problems over here, and I'm sharing the questions with the answers also, so that you can solve them and cross check through your answers whether it is right or wrong. See, I'll just explain the question to you. The two single phase transformers A and B of equal voltage ratios are connected in parallel and supply a total load of 500 amps at 0.8 power factor lagging. It is secondary terminal voltage of 400 volts. The equivalent impedances of transformers referred to secondaries are 2 plus J3 ohm and 2.5 plus J5 ohms respectively. They calculate the current supplied by each transformer. Nothing but IA and IB. And you know the formulas for IA and IB. IA is equals to total I into ZB by ZA plus ZB. And for IB it is total I into ZA by ZA plus ZB. So you have the equivalent impedance of transformers referred to secondary. You have ZA and ZB, and in parallel supplying a total. This is the total current. We need to find IA and IB. It's very simple. Just do it and cross check the answers. The next question number 2. Here also this is also a problem. I'll just read it out for you. The two single phase transformers A and B operating in parallel supply with a common load of 500 amps at 0.8 power factor lagging. The transformer A is rated at 750 kVA and its percentage ratio and percentage resistance and percentage reactances are 3 and 5 respectively. And for the transformer B is rated at 500 kVA and its percentage resistance and percentage reactances are 2 and 4 respectively. And here you need to find the current supplied by each transformer. Similarly, IA and IB. And you have the answers over here. Just try to solve the problem and cross check the answers whether you are right or wrong. Okay, fine. That's it for the today's session. Thank you one and all.